Hello again, grade 8s. In today's lesson, we're going to look at how we can calculate the total number of possible outcomes of an experiment, but we're going to focus more on how to do this without actually constructing a table or a tree diagram, which could potentially save us a little bit of work. So it's kind of like an alternate method to determining the total number of possible outcomes. So let's start off by considering an experiment which would be familiar to us. So we're going to take a coin, we're going to flip it, and then we're going to roll a six-sided die. Now, the total number of possible outcomes for this experiment would be, well, if you flipped a coin, there's two possible outcomes. You either get heads or you get tails. So the two possible outcomes for event number 1, which is the coin, would be 2. If you roll the six-sided die, there's 6 possible outcomes because you could roll a 1, a 2, a 3, a 4, a 5, or a 6. So flipping a coin, there's 2 possible outcomes, and then rolling a die, there are 6 possible outcomes. Now, the way we would have done this in the last 2 lessons to determine the total number of possible outcomes would have been to draw a tree diagram or a table, and then count the number of entries in the table or the number of branches on the tree. So yeah, we could represent the sample spaces of the table or tree diagram and then count the total number of possible outcomes. So let's say we actually constructed a table to do this. So on the table, you have your rows represented by event number 1, that's the coin flip, and you have heads and tails. And then event number 2 would represent the columns, which would be the die, which has events 1, 2, 3, 4, 5, 6. And then what we do is we'd match up the rows and the columns to identify my possible outcomes as H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. And then to figure out the total number of possible outcomes, you just count all those individual table entries. So that would be 12 possible outcomes. And I'm abbreviating, and again, we abbreviate possible outcomes with the acronym PO. You could also construct a tree diagram, and we would count 12 total branches on the tree diagram to determine the possible outcomes, or write the sample space down, in which case we'd have 12 outcomes listed in all the different brackets. Now, there is another way you can do this without even having to actually without actually needing to draw the tree diagram or the table. So if my events are independent, and again, if independent means that the outcome of event 1 has no impact on the outcome of event number 2. So again, flipping a coin and landing on heads has no influence on what the die is going to land on. So we're going to call the total number of possible outcomes for event number 1 PO1. We'll use a little subscript 1 to indicate it as event number 1. And then my possible outcomes for event number 2, we're going to write down PO2. So if I want to calculate the total number of possible outcomes, all I have to do is take the total number of possible outcomes for event 1 and multiply by the total number of possible outcomes for event number 2. So with the example I just showed here, if we did this, well, how many possible outcomes are there for flipping a coin? There's 2 of them. How many possible outcomes are there for rolling a 6-sided die? There's 6. So if I take the possible outcomes for event 1 and multiply by the possible outcomes for event 2, I'd have 2 times 6, which would also give me 12 total possible outcomes. Again, I could have done that calculation without having constructed a table or a tree diagram. So again, it's just a much, much faster way to actually figure out what the total number of possible outcomes in an experiment are. Now, doing problems like this would be a little bit too simple. So we're going to add a little bit more of a complication in. Let's say we have 3 independent events. So we do 3 things one after another. If you want to calculate the total number of possible outcomes in an experiment where you had 3 independent events, we could actually calculate it by this. We take the number of possible outcomes for event 1, multiply by the number of possible outcomes for event 2, and multiply by the possible number of outcomes for event 3. And that would give you my total number of possible outcomes for the entire experiment. And we're going to focus on this in our example problem, an experiment that has 3 possible outcomes to it. Okay, so a coin is flipped a spinner is spun, and we can see the spinner at the bottom of the page here, and a four-sided die is rolled. So I actually have three things that I'm doing here. Okay, so it says, first of all, let's identify how many possible outcomes there are for every single individual event. Okay, so we can go ahead and do this. So A, okay, event number one would be this one, flipping the coin. So flipping the coin, how many possible outcomes are there? So the possible outcomes for event number one would just be equal to 2. You can either flip heads or you can flip tails. Event number 2 is going to be the spinner. So this is event number 2. So the possible outcomes for event number 2 would be, look at the spinner. There's 3 sections you could land on. So there's 3 possibilities. You're either going to land on A, you're going to land on B, or you're going to land on C. And then event number 3 is going to be the four-sided die. And again, that four-sided die is just, it's a pyramid, but it's got a triangular base to it. So this is event number 3. So then I could say the possible outcomes for event number 3 would then be equal to 4. It's a four-sided die. You can land on 1, 2, 3, or 4. Now, B says calculate the total number of possible outcomes. Now, if I didn't just show you that previous equation, we would need to actually draw a tree diagram or a table to do this. Although in this example, the table actually doesn't work. But we can use that equation I just introduced to you. So here's how it works. Okay, so B, the total number of possible outcomes would be equal to the possible outcomes for event number 1 multiplied by the possible outcomes for event number 2 multiplied by the possible outcomes for event number 3. This would be equal to, okay, so for event 1, there's 2 possible outcomes, heads or tails. Multiplied by the possible outcomes for event 2, which is the spinner, 3 possible outcomes. You can land on section A, section B, or section C. For event number 3, four-sided die, we can land on one of 4 sides, so we'd have 4 possible outcomes. And then all I need to do is multiply all those different numbers together. So 2 times 3 would be 6, and then 6 times 4 would be 24. So without even drawing a table or a tree diagram, I can actually calculate the number of possible outcomes just by multiplying the number of possible outcomes for each independent event together. Okay, now we're going to confirm that this actually does work, though. So C says confirm the result in A by representing the sample space with the tree diagram. Okay, this is a nightmare. When you're trying to do a tree diagram that shows 3 different possible events, because you're going to have a ton of different branches and trunks to draw here. Okay, so we're going to give ourselves a ton of space to actually do this. Okay, so first of all, let's write down the name of event number 1. So that's going to be that's going to be the coin. Okay, and then we have the spinner. And then we have the die. And this is part, I think it's part C. Okay, so again, lots of space here. So I'm going to write down heads. I'm going to write down tails. Okay, so we're going to start with the trunks of the tree as 2 different trees. We have heads and tails, the outcomes for the coin. And we're going to branch that into the outcomes for the spinner. So the spinner can branch into outcome A. It can branch into outcome B, or it can branch into outcome C. And the same with the tails. Tails can branch into outcome A. Tails can branch into outcome B for the spinner, or it can branch into outcome C for the spinner. Now, I then need to take the outcomes for the spinner and then break them into even more branches on the tree. Okay, so for example, this branch A could branch into, on the die, you could branch into 1, could branch into 2, branch into 3, branch into 4. You can see here how you can run out of space very quickly. Okay, B goes into 1, B goes into 2, B goes into 3, B goes into 4. And then C goes into 1, goes into 2, goes into 3, goes into 4. Okay, and that's only half of the actual tree diagram. And this actually isn't even that bad. There's not even that many possible outcomes for this experiment. Okay, so then this one, same thing. We can go tails, then A, and then we can go into 1, 2, 3, 4. B can go into 1, 2, 3, 4. I thought I gave myself enough space. Evidently not. Okay, C can go into 1. It can go into 2. It can go into 3. And it can go into 4. Okay, so that's the tree diagram. And it said, draw the tree diagram and confirm that there are the same number of outcomes we calculated in part B. Well, part B told us we had 24 possible outcomes. If you count the number of branches on the tree, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that is correct. There are 24 possible outcomes when you actually do this. Okay. Now, part D says, explain why the sample space cannot be represented with a table. So you actually cannot draw a table to represent this. It's impossible. Now, the issue with the table is the table is made up of two parts, rows and columns. Rows can represent one event, columns can represent another event, but what would you use to represent the third event? The table isn't designed to handle a third event because the maximum thing you can have is rows and columns. So maybe the way I would just justify it here is I would say in a table, the rows represent event number 1 and the columns represent event number 2, which is a maximum of 2 events. There's nothing in the table that could be used to represent the third event. So table would not work here. So which is a maximum of 2 independent events. Okay, E says determine the probability of flipping tails, spinning a consonant, and then rolling at least a 2. Okay, so let's clarify what some of this language means in case you're not familiar with it. Okay, first of all, if you're not familiar with that word consonant, oops, let's spell that correctly. Okay. consonant. A consonant is a letter of the alphabet that is not a vowel. And obviously your vowels are A, E, I, O, or U. Okay. So if you look at the spinner, so which letters on the spinner would not be a vowel? Well, that could be B or C. B or C are consonants, okay? So we could write down B or C. And then it says of rolling at least a 2 on the die. Again, if you have that language, it says at least 2. At least 2 means that's the lowest number that is acceptable. So that could be greater than or equal to 2. So which numbers on the die would be acceptable? Rolling a 2, rolling a 3, or rolling a 4. Okay, so let's go to the tree diagram now and try to circle which would fall into this category. Okay, so first of all, we're flipping tails. So we're gonna focus just on this part of the tree. So tails. We're not allowed to have a vowel, so we're gonna focus on this and this, tails, and then B or C. And then we need a number that is going to be greater than or equal to 2. So we can have 2, 3, or 4, 2, 3, or 4. So there would be 6 possibilities where you flip tails, roll a consonant, and get a number that is at least 2. Okay, so let's calculate this now. So I can say the probability of flipping tails, spinning a consonant, and obtaining a number which would be greater than or equal to 2 on the die would be equal to the number of favorable outcomes divided by the number of possible outcomes. How many possible outcomes? There's 24. We actually calculated that before we even drew the tree diagram. How many favorable outcomes? Well, there'll be 6 of those. Okay, so 6 over 24. Okay, I'll write the work on the next line here because I've run out of space. 6 out of 24 gives you a nice terminating decimal. It gives you 0.25. And then if you take that and multiply by 100 to turn it into a percentage, you would then have 25%. Okay, so as you can see, if you have 3 independent events, the tree diagram becomes quite nightmarish to actually draw. And then it gets a little more complicated because you really got to keep track of all the different events. You start to do a probability calculation afterwards. All right, so that's it for this lesson. And you can complete the assignment in the probability workbooklet that is called Calculating Possible Outcomes. And I will talk to you in the next lesson.